Today I'm going to show you how to set up and simulate a simple hollow tube compression in LS-DYNA to look something like this. So we're going to be doing everything within PrePost, so we're going to be making the mesh and everything that's required to do this simulation here so that anyone can do it, because PrePost is free to download for anybody. So first we're going to make the mesh of this 2D cylinder. So we're going to go to Mesh, Shape Mesh. You're going to click this entry, go down to cylinder shell, and then here is where you're going to be able to define your radius of the cylinder, the length of it, and the number of elements along the circular direction, as well as the number of elements along the length. So let's just throw some numbers in. Let's make it 100 long, 30 millimeters in radius. And then down here, you're going to specify the initial location of the start of the cylinder. We're just going to use the origin, so 0, 0, 0. And then this is where you're going to make the direction. So this is the direction along the length of the extrusion, basically pulling the cylinder out. So let's just create one and just show you. So we did a normal direction in the x direction, which is why it's facing the x direction this way. We've got a radius of 30, so this is 30 millimeters wide, and this is all going to depend on whatever coordinate system, or not coordinate system, but unit system you want to use. We're just going to use millimeters, and that's going to determine what your material is going to be and all the different parameters in there. If you need any assistance on that, just look up online different types of SAE coordinate systems and just make sure your units are consistent. So if you have millimeters and then seconds, your velocity is going to be millimeters per second, and so on, and then that's going to transfer all the way down to force and whatever your mass is. So just make sure you're using consistent units. But getting back to this, whenever you mesh something, you want to make sure you've got a good aspect ratio for elements. So this is going to give you a preview of what this mesh is going to look like with the parameters you have in here. So with these parameters, we kind of have this skewed rectangular element. We want to make sure that these are squares if we're using quads. So what we're going to do is increase the number of elements along the length. So let's make this 10, and we're going to reject what we have and then recreate it. So now we have something that's a little more square. And if you're ever doing compression analysis, you will also want to make sure you have some pretty fine elements, I guess, but not too fine. Just depends on what your computer requirements are, or the abilities of your computer are. So in this case, we'll make it a little more. So let's go 20 along the length and 40 along the circular region. There we go. So that's a little better. And if you like what you have, you can come down here and give it a target name. So we can call it cylinder, and the part ID is going to be 1, start of the element IDs is going to be 1, start of the node IDs is going to be 1, and then you're just going to accept it. And there you go. There's your cylinder, and it's going to automatically make this part. So if we click done here, we're going to go to model in this master toolbar. So off of here, you're going to have the sub toolbar pop up as you click things. But we're going to go to model and then keyword, and this is where all of the makeup of the model is going to be stored in the keyword, and it's just easy to access here. And this tab is going to show only what's in your model if you have this selected. And it's an easy way to kind of make sure that you collapse everything so you don't have a lot of stuff, because if all is on, it's going to show all the different options to do different things in this program. But we do need all to set up the model. So what we're going to do is go to part, because this is a part, and it's going to automatically make this part, and we gave it the name cylinder, and it's part ID 1. So 3 things every part needs that's in a model is a part ID. You also need a section ID, and you need a material ID. Everything else is optional, and I can get into that later, but you can just leave them as default for now. So the section ID, if you want to create one, you can click this button here, and if you don't, so what this button is going to do is allow you to select any that are already in the model and defined. But right now we don't have any defined because we're just starting out brand new. So you can click new keyword, and what it's going to do, it's going to automatically make a section for whatever type of mesh that you have. So in our case, it's a shell mesh or a 2D mesh, so it's going to make a section shell. What the section is it defines how each of these elements for the finite element analysis, how it's going to respond mathematically to different boundary conditions. So it's the math behind the simulation. And if you need to make a section, you can just do new ID, and it's going to give it a section ID of 1. EL form is your formulation for the math, basically. You can leave it as default for now, but if you have a really complex simulation, fully integrated elements allow for more accurate analysis. However, they're more expensive, but for now we're going to leave it as default. These things are all optional. The only other thing you need to define is your thickness. So this is the shell thickness of each of these elements. So if we zoom in on this, see it's a shell, and in LS-DYNA you have to define a certain thickness. Now it can be whatever you want it to be. You can make it 10 or you can make it 1. It doesn't really matter, or I mean it matters, but you can define it however you want, and this will be representative to how thick this cylinder actually is. So if you have a real life test like a straw, we can go like a straw, you'd measure how thick this edge is in the straw, and then you'd prescribe that thickness. So this will actually be pretty accurate. So we're going to go here and we're going to give it a thickness of 1 millimeter, and whenever you put in a thickness in the first T1 and you hit enter, it's going to prescribe it along the other 3. And these are thicknesses at different nodal locations for each of the elements. Just leave it at standard across the board. If you ever do variable thicknesses, you wouldn't really want to do it here. You'd want to do it in some sort of mapping, so you can have varying thicknesses along a geometry. That's possible, but I'm not going to do that. And then another thing to keep in mind is in-lock. This is how the thickness is defined for each of the elements. What this means is it's going to extrude the thickness in different ways. So in-lock of 0 is going to be a mid-surface, so it's going to extrude the surface 0.5 this way, 0.5 this way. If it's top surface, it's going to go one direction. If it's bottom surface, it's going to go the other direction. This is just going to determine how the shells respond. It's just going to affect it a little bit. But once you have it, hit accept. Then we're going to have to make a material. So what you can do is you click this button, go to new keyword, and it's not going to automatically make a material here because there's a bunch of different materials that you can give any model. But I mean, there's so many, and some are really complicated, some are not really complicated. And if you're just trying to learn, I would suggest sticking with something easy like elastic, where all you have to input are things like density, the Young's modulus, and the Poisson's ratio. So that's what we're going to do, and we're going to do new ID. So we're going to have a material ID of 1, and the density, we're going to make it water, so 1e to the -6 in our unit system. Our unit system is, so we're going to say units, is kilograms, millimeters, milliseconds, gigapascals, kilonewtons, and newton meters. And this is not, just me typing this in is not going to define them for the model. There's no way in PrePost to actually define units so that everything you type is in those units. It just is consistent across the board. So if you have mass, it's going to be in kilograms. If you have distance, it's going to be in millimeters. If you have time, it's milliseconds. And if you keep these consistent, it's going to define the rest of the units for you, if that makes any sense. But for now, density is going to be density of water. So we're going to define the elastic modulus as 0.1 or something similar to rubber. If you're looking for examples, you can just Google it and find out whatever the material is that you're looking for. That's the benefit of using a mat elastic, because everything in here you can actually find by just Googling it. Or if you're actually doing material testing, then you'll have it that way, because you'll have some response data and you can actually fit a material model to your experimental data. Poisson's ratio, let's just say 0.45. So we're going to hit accept. So now we have our part with a section ID, which is defining how the elements are going to respond, and the material ID, which is the material that each of the elements are defined as. So we're going to hit accept, hit done. So now we have our part. So now we're going to need to set up the actual boundary conditions of the simulation. And what we're going to do is do a compression of the, an axial compression of this cylinder. So we're going to go to create entity here, and create entity allows you to define different sets. You can also define other things here, but I mainly use it for defining sets. And we're going to make a set node. And what we want to do is make two different sets of nodes, the bottom and the top, where we're going to have the bottom stay constrained in the x direction so that this can't move down, but can move outwards. And we're going to set a top node set that is going to define the motion of this cylinder compressing. So we're going to go up here to create. One's fine, and we can name this bottom constraint. And then this is your selection box, which is going to determine how you can select different things. So if it's pick, it's only going to let you pick one node at a time. You can hit clear to clear everything out. Area allows you to drag and select a bunch of different things at once. It goes through, so it'll select through if you want. And there's a bunch of different ways you can do it. So you can go by element and then propagate along at an angle, which is useful in certain circumstances. But in this case, we're just going to use area and by node. So what we're going to do is select the bottom row of elements or of nodes and hit apply. So that's our bottom constraint, or it's not our constraint, but that's going to be used for our bottom constraint. And then we're going to have top compression, and we're going to make this one set 2, and we're going to hit apply. So now we have our two sets, and what we want to do is set up the boundary conditions. So in our keyword, we're going to go to boundary, and we're going to go to a thing called boundary SPC Set. So SPC stands for single point constraint, but we're going to do this for a set of nodes. So each of these nodes is going to be constrained however we define here. You can give it an ID if you want, but you don't have to. You can just click this dot and then select whichever constraint you're looking for. So we're going to do the bottom first and hit done. And then this is how it's going to be constrained. So this is linear X, linear Y, linear Z, and then rotational up to 3 as well. So the value, 0 means there's not a constraint on it, it's free to move in that direction. 1 means that it's constrained in that direction. So all we want to do is constrain it in the X direction so that it can't move downward. So we're going to make that 1, and then we're going to hit accept. We're also going to make a new one. Wait, no, we're not. We're going to go to our prescribed motion. So what we're going to do is make a boundary prescribed motion for the top and define it as a compression motion downward. And that is boundary prescribed motion set, because we're going to use this set of nodes. And we're going to hit new ID, node set top. And then our degrees of freedom are the direction that the nodes are going to move in. And we want this to be an X translational degree of freedom because we want it to move downward in the X direction. So we're going to leave that at 1 because it's equation 1. VAD is determining if this is velocity, acceleration, or displacement. I usually use displacement because it gives you a lot of control. So we're going to do displacement as equation 2, because what this means, if this thing's 100 millimeters tall, we can say we want it to move 50 millimeters, so halfway down in a certain amount of time. And then you can do the math and do different velocities however you want, or different accelerations. But if you set it at a certain speed and make the termination time too great, it may bottom out. So I like using displacement. The LCID is actually the curve that is going to prescribe this motion. We don't have any available right now, so we're going to have to make one. And we're going to double click curve, and then new ID, and then this is the values of the curve. So this is going to be a simple curve. We're going to have the first one at 0, 0, and then you're going to hit insert, and it's going to insert these two values. The first one is your time, and the second one is going to be your displacement, just because we're using a displacement VAD here. If this was set at 0, or if it was set as velocity, this would be time, and this would be velocity, if that makes sense. So we're going to do 50 milliseconds and 50 millimeters of compression, and then insert that. Then we're going to hit accept. And then if you go back to your, if you click these, it actually opens up the corresponding curve. You're going to plot it, and this is our curve. So we're going to go from 0 milliseconds to 50 milliseconds, and we're going to move 50 millimeters. So it's just a linear motion. So now we have the motion set up, and make sure you hit accept. Don't just hit done. We've got the motion set up, we've got the constraint set up, and we have our model defined with material properties. And the last thing we need to do is set up the guts of the simulation, like what's going to happen, or how you're going to get data out of it. So again, if you use model, it'll collapse everything, and then you can just minimize things so that when you hit this, it's not so gigantic. So what we're going to do is first go to control. This is something every simulation needs. You need to go to control, termination, and this is going to define how long each of these simulations are going to take in simulation time, not real time. So this is going to be a 50 millisecond event, and you don't have to do anything else, and you can accept. Done. So now we have our control termination at 50 milliseconds because our curve is going 50 millimeters in 50 milliseconds. This doesn't have to match the boundary prescribed motion, but we're going to do that. So if we set this at 100 and the displacement was 50 milliseconds with 50 millimeters, there would just be a 50 millisecond period after the event where it would just be not doing anything. So then we need to define our outputs, and this is in database. So if you go to database, we're going to go to ASCII option, and then here is where you have a bunch of different options on how you want data to be able to be extracted out of the model. If you click on each of these, you'll get kind of a definition, and you can Google it and actually look in the manual to see what the what each of these are going to output. So what we're going to use is let's see, node out is nodal displacements, velocities, and accelerations, because we want to track the displacement of this node set downward, because we want to look at the force deflection curve. And then we're also going to look at SPC force. Am I blind? Here it is, SPC force. This is the SPC reaction forces, which will be the forces down here. And for backup, you can also say boundary conditions out forces. For each of these, you need to give a frequency of how often it's going to output data. So general rule of thumb is to go more than 100 for your simulation, probably higher than that, but since this is a demonstration, we're only going to go 100. So if our simulation is 50 milliseconds, we're going to make this 0.5, so we have 100 outputs for the entire simulation. The greater you make this, the more data is going to be stored, so the larger the output file is going to be. Some of these can be gigantic depending on the model. And you're going to need to do this for all of the ones that you've checked. So 0.5 for B and D out, 0.5 here, and 0.5 here. And then you're going to hit accept and done. So now you have your outputs. So then one more thing we want to do is to add a database binary or database extent binary card, which is here. And what this will allow us to do is to activate different flags to get different types of data out. And what this is in particular is the strain flag. So if you go to this option right here and make this 1, what it's going to do is it's going to write out the strain data to the D3 plot, so like a visual, kind of like a heat map, and to the EL out or any type of data that you want to get out. But we're mainly going to use it for just looking at a fringe plot heat map of the strain. So whenever you make this 1, you can hit accept, and you can also read through what these other options are, and they may be useful for whatever you're going to do. But for now, we're just going to work with this, and all of this information is available in the manual. So then you're going to hit save, and there you go. One thing to remember though is each of these outputs needs to have a corresponding thing in the model, and what we need to do is define a sort of sensor for tracking this set of nodes, because we want to get the node outs here. But in order to get these, you have to define it in database history. So we're going to go to history and history node set. So what this is going to do is going to, so top compression, this is going to track this node set throughout time and output data every 0.5 milliseconds. And it's only going to do that if you define it here in database node history set. Now, one thing that you can do is there's a way to track the actual animation nodes, which is usually a lot coarser than this frequency is. But general practice is to set these databases to track nodes and forces. And save. You change that frame rate for your animation in your database, and it's binary D3 plot here. And the DT is the time interval between each visual output. So it's going to be like a movie where you're going to have one frame for every millisecond that you put in here. So we'll say if it's a 50 millisecond simulation, we can just say 2 is fine. So a frame is going to output every 2 milliseconds. You hit accept and then done. And that's the simulation, so we have it already. So once you have your simulation set up, you can go to File, Save As, Save Keyword As, and what we're gonna do is, you can save it as whatever you want to call it. So let's say cylinder compress, and you're always gonna want to put .k. These files are .k or also .key. And they can also be .dyn, so dyn, but we're going to use it as .k, and then you can hit save. And then in advanced, you can select different aspects of it that you want to save, but we want to save everything that we made, and you can hit save. So here's your file once you save it, and to check it, you can open up a new window of PrePost. You're going to drag it in, and there will be errors that pop up if there was an issue. But we didn't have any errors, and you can also go to display here in model and make sure that everything that you want is in here. So your SPC node set is here, which is going to prevent your nodes from moving, and your boundary prescribed motion is here. One thing that I did forget is the coordinate system. So make sure you always remember where your coordinate system is pointed, because if you remember, we made our curve, so our defined curve for our boundary prescribed motion, we made it positive. So actually what's going to happen if we leave it like this is this cylinder is going to stretch instead of compress. And an easy way to fix that is to go here, and these are scale factors. So SFA is your scale factor for your A column, SFO is your scale factor for your O column. And if this is positive, all you need to do is make this -1 and then hit accept. And now if you plot it, it's negative direction. So now we're going to get that compression that we want. But once you changed it, you got to resave it. So if you open something and you save it, and you just want to override it, you can just go to save and save keyword, and then just going to override it. So now we want to run it. So you're going to go to your folder, and you're going to open up your LS-DYNA manager, which looks like this, and then you're going to go here, browse, and then you're going to find your model. You can leave everything else for now, and then you're going to hit run. And when you hit run, something's going to look like, doesn't show up if I have it on this window. It'll look like this. It's going to show all of your outputs, and you're writing normal termination. So this means that the model worked if it's normal termination. So now you have your output files, and these are what we wrote as outputs. So you have your BND out, which is your boundary conditions out, your node out, and your SPC force. D3 HSP is like a overall file of what happened, similar to what this gray screen showed, and your D3 plots are the animation. So if you click the D3 plot that doesn't have a number and you drag it in, it's going to open up the animation. So if we open it up and we go to play, it's going to look like that. It smashed it. So this is an example of something that you wouldn't want it to look like. So I've actually tweaked some things since that last simulation because this type of stuff happens. And I actually didn't test that before I ran it. But this is what happens with this type of stuff. You'll run something and it looks weird, so the boundary conditions weren't right, or the materials were too soft, or whatever. And this is just an example, so I'm just messing with stuff to get something that may be helpful. So what I actually did was added some things, and for background, everything in this model, so everything in your keyword is stored in this K file. So if you double click it, go to Cax Edit. This is a text reader that I use, and it's pretty helpful. It lets you like collapse everything. So everything in here is what we just made in the model, and it's in text format. And this is the easiest way to modify things once you have it in here. And I would highly suggest getting used to the text format. So so for example, if you want to change the termination time, you could just change it to 30, save it, and done. You don't have to export it from here. You can just change it straight from here. But what I did was I made a second SPC set for the nodes on the top that are moving. I made this extra set to constrain the motion from rotating in the X and Y and Z directions. So this only has translational motion. And I did the same thing for the nodes on the bottom to keep these nodes normal with the compression, which will kind of help the aspect ratio. I also went to the elastic material, and I made the elastic modulus 1 instead of 0.1 to stiffen it up, since it looked like it was a little too soft for this simulation. And I went to the section shell and increased the thickness of the 2D shells from 1 to 3, and that is here. So I made these 3 instead of 1. So, and from that, I just ran it, and I got so I ran it, and if you open it up now, I got this simulation. So it starts compressing evenly, and then right here at around 6 milliseconds, the cylinder buckles. Something you'd see in like a straw if you took this and axially compressed it. It would buckle at some point, and then if you keep clicking forward in the frames, it's going to buckle even more and bend. So for demonstration purposes, I made these not be able to rotate. If they were able to rotate, this would probably be bending on itself and look all weird, and that may be realistic, but for example, I just wanted to show something that doesn't look so terrible. So and in a complex motion like this, where you've got these shells, and in that last one, I don't know what happens, but when you got these shells sort of bending like this is where using different element formulations actually helps a lot. So if these were fully integrated elements, they may not deform so weirdly, and a lot of this is called hourglassing, where you have elements deforming in unrealistic ways. And I can get into that later, but this is just an example. This was more complicated than I actually thought it was going to be. And we don't have any contacts made, so here at the end, it actually starts intersecting itself. So that would be the case of adding a contact, which would prevent that. But it's not a big deal. If you wanted to add a contact, you can open up your model. And I realize this is a longer video, but long videos like this may be helpful for somebody who's really just banging their head against the wall. So if you wanted to add a self-contact with this part, so it's not contacting anything else, it's just contact with itself, you can go to keyword, hit all, go to contact, and this is a contact means it's going to interact with something. We're going to make automatic single surface, and what we want to do is make this part in contact with itself in a single surface contact. So let's make, so when you open up a contact, this is what it looks like. It may look confusing, but your SSID is the slave of the contact, which is, think of it kind of like the thing that's getting impacted, and the master is the thing that is impacting. That's a simple way to explain it. It may not be correct, so don't crucify me over that, but that's just the way I'm going to explain it for now. There's ways that you need to do this to match up element sizes or whatever, but just think of it like that for now. And whenever you click these, you can actually, each of these has a type, so that the slave has a slave type here. So the different equations are different types of objects that will be impacted. So you have segment sets, part sets, and part IDs. So this is going to be a part ID, and we're going to make it 3, so equation 3 part ID. So then here we can click this button and you can click the part that's going to be in this contact. And since this is a single surface, all you need is the slave. You don't need a master. And then here's some friction. We'll leave it frictionless for now, and then these are scale factors. So that's a simple contact we add in, and then we can hit done. And what we're going to have to do is resave it. So go to File, Save, override it, and then we're going to go back to our manager here. And if you already ran something and you haven't changed the name or the location, you can hit this circular run button, and it's just going to rerun the last thing that you did with the same like memory requirements. So if you hit that, hit OK, it's going to rerun it and normal, and then we'll reopen it and we can see if that contact worked. So you drag in your D3 plot, open it up. And I don't know what's going on at the end there. It's like going past termination time. Sometimes stuff like this happens. It'll just take some time to look into it, but it's also not a big deal if it's past your termination time. Like if you're just taking data up to this point, it doesn't really matter. But yeah, look, the contact worked and there's no more self-penetrations, which is good. And then from here, if you want to look at the actual data, which I can't believe I'm just getting to this, you can go to ASCII because we made them ASCIIs. No doubt we can get the displacement of the top nodes. What you can do is hit load, and then see if I can pick a node. So whenever you pick through these, you click highlight, and it's going to highlight the different nodes. So you can click them all and average them if you want. So it's going to pick all of them in the set, and you can go to X displacement and plot. Let me blow my computer up. Is it because highlight's on? That's weird. So some versions of PrePost are kind of strange, but if I have highlight on, it won't plot this, but if it's off, it will. But regardless, you can click one of the nodes, and this is like this node on this top. You can also click them all and plot all of the displacements. And they're all the exact same because they're all prescribed the same motion. So it doesn't really matter. We can just do one. And if you have it, you can go to Save. And what you can do, if you want to cross-plot this with your force, you can save it as a curve file and then access it later. If you just want it as a CSV, you can go to CSV and then type in your file location and save it. But we're gonna cross-plot it. So let's call this displacement, save, exit out, go to your force, so SPC force, load. We're gonna do all of them. We're gonna do X force, or we can do resultant. So this is where this is where frequency really comes into play. So we only had 100 points for our whole simulation, so that's why it looks like this. I actually didn't do this right. So if we made a set, so what we can do is click set ID here, and then we can click the set, and then click resultant, and then plot it, and then it has a averaged out plot here for us, which still you can left click each of these points to kind of see values, which still isn't very, it's pretty coarse, so you have a lot of, this. But We want to save it, so we're going to save this as force, save. And then if you have two plots and you want to cross plot them, you're going to go to XY plot and then cross, and then it's going to have x-axis. You're going to click your x, which is going to be displacement in this case, and then it's going to go to y, and you're going to go to force, click force, and then plot. And this is actually in the negative x displacement, so if you want this to be positive, you can go to scale and then x scale, make this negative, and then apply. And now it's over here, and you can change your window to be positive now, and then hit apply. But I keep I did. I'm dumb. Make this 0, and then this is going to be 50. There you go. So here's our force displacement, and it's going to actually put the cross-plotted values here. And then if you want this as a CSV, you can go to Save, Single Axis, which is going to make it a single x-axis and a single y. If you have multiple values, you can do single axis if they all have like the same, but I don't even know why I'm confusing you. So we're going to call this force v displacement, and it's going to be a CSV, so save. And now in your folder, you've got force versus displacement, and you can open it in Excel, and there you have it, and you can plot it. Or you can open it in MATLAB, whatever you want. So the last thing I want to go over are just some tricks, and also a way to actually visualize the strain output like we set up for the D3 plots. So if you have the D3 plots open, this is your animation toolbar, which you kind of went over, but if you drag this, it'll view the last point wherever you let go. But if you click animate here and you drag, you can actually like scroll through the frames like this. You can also hit play to actually play it, and you can slow down to change this to a number of frames per second, and it will slow down the animation. You can also search for specific states or frames here. So if you know your video's got 30 states and you want the middle one, you can type 15, hit enter, and it'll take you to state 15. And if you want the nodes at a specific frame, you can go to output and do entire model, nodal coordinates, hit current, and it's going to tell you, it's going to export the nodes from this state, and then you can write it as a as like the nodes at a certain location. So if you have like a preloading and you want to make sure that the impactor is touching wherever it's going to be, you can export the nodes whenever the nodes are where you want them, and like the object is how you want it, or it works with like settling, foams, and different things like that. It's just a useful trick to know. Another thing that I mentioned before is history. If you don't have something in a ASCII bin, or not bin out, but an ASCII output, so this database outputs that we set up, you can still track certain things through the history, and this is going to give you a data point for every frame that you have. So this will only have 27 total or 26 total points. And you can do things like coordinates, displacements, similar to what we already had. So if you look at x displacement and you hit plot, it's going to give you the same line. It's just going to have less points than what we set up. So this is useful if you forget something and you forget to set something up in an ASCII database output, and it's something simple like a linear displacement like this, you can still get it out using the history. So that's useful. So now if we want to look at the heat map of the strain for this cylinder during compression, you can go to fringe component up here within the post tab, and then here you can select a bunch of different options to visualize. You can look at your stress, your strains, different types of each. Now it's important to remember in pre-post it defaults to output your true stresses and true strains, which may be different than data that you want to compare to, because usually data is looking at engineering stress and strain. If you want to look at engineering strain, you can use infinitesimal, and then you can look at something like first principle strain here, and then click through, and it's going to give you a strain history. But you can also just go to the normal strain or stress and then convert any output after. But if you actually want to have a video, you want to make sure it's in the correct units that you're comparing to. So we'll go ahead and go to infinitesimal, go to first principal strain, and then you can go to fringe range here, and it's going to automatically change the range. Like the default's going to be dynamic, so it's going to change the max range for the heat map as it goes, which is kind of silly to me. So what you want to make sure you do is go to user, active parts only is fine, this is all we have, and then you can manually set the max strain. One thing you can use dynamic for is to actually find the maximum strain for the simulation. So if you click through, it's going to change the maximum strain for the total model at each of these time points. So something like ballpark is around 12% strain that we can see. So if we want to back this out, go to user, set our max at around, we can just say 10, or that's 0.1. Hit assign and then update, and then what it's going to do is, there it didn't, see, number 1, update, there we go. So then it updated the heat map range. So if we play it through, it's going to show the strains at these different locations. So you can really localize the areas of highest strain if you want to. Then you can decrease this if you want. Like if it's too localized, you can decrease it even more, hit update, right? And now you really have some red areas. And if you want to present this to a class or to a sponsor or a conference or whatever, you want a nice video, right, of this compression. Maybe not that fast, but you want a nice video. And one thing to keep in mind is that it can be useful to increase your D3 plot frequency so that it doesn't look so, choppy, and then you really get a nice looking video. But if you want to export a video, what you can do is go to File. When you're in your D3 plot, you go to File, you go to Movie. You can select whatever type of format you want. Make your frames per second whatever you want. It's pretty quick if you have it at 30, so we can just do like 15 for now, I guess. You can set your location, whatever's fine, change the name, so strain, what we call it, engineering strain, and then you can hit start, and it's going to output as a video, and what it'll look like is something like this. There we go. Okay. You can also turn off the mesh if you want, make it look even better, and get something like that. But those are just some tips you can use, and I think that's it for this video. It's been long enough. I hope it's been helpful. Let me know if there's any questions anyone has. I'm always looking for suggestions. This was actually a question somebody had on one of my other videos, so I try to answer them, but I'm a little slow getting to them because I have a busy schedule outside of doing this. But I'll try to get to any questions that anyone has, and thanks for watching, and see you next time.